Good afternoon, everyone. Welcome to my class again. It's going to be an interesting time as we start this. We'll continue from where we stopped last time on the concept of thermodynamics. And you see, we have an interesting, some interesting lesson objectives this today. The topic again is thermodynamics. We have seen the introduction to thermodynamics as an important concept in physics. Today we're looking at heat transfer and energy calculation. Under this topic, we'll be having about 5 lesson objectives, but we might not really finish up the lesson objective today due to the constraint of time and also for you to be able to understand the concepts. So we're going to start from the first learning objective, that is for you to be able to define heat, temperature, and internal energy at the end of this lesson. Then to understand and apply the first law of thermodynamics. The first law of thermodynamics states that there is no energy change, there is no energy interaction in a closed system, that no energy loss and no energy gain. So then also explain and calculate energy changes during heat transfer. Then we said how to solve problems using specific heat capacity to solve problems. They analyze different heat transfer methods, that is conduction, convection, and radiation. So we quickly go into what we have for today. Today, as I've said, we're going to look at all of these learning objectives. And so I want you to pay rapt attention. So let's look at the first learning objective, heat and temperature. What is heat? What do you understand by the word heat? We'll be saying, oh, this thing is hot. Oh, this thing, what is heat? So when we talk about heat, let me break it from the fundamental concept that result into what we measure as heat. So we, in physics, we believe that, matter are made up of particles. And these particles, they are in constant interaction. They are in constant motion. And when an object is in motion, the energy possessed by object in motion is kinetic energy. So when we now talk about heat, because of this particle interaction as a result of the movement of the particles, then the result is heat energy that we see. And so we can define heat as when energy is transferred from a body from one body to the other as a result of the temperature difference. The temperature difference. We can also say the summation of the total kinetic energy, the summation of the total kinetic energy in a body. That is our heat, and it's measured in joule. It's measured in joule because it's a form of energy. Then temperature. What about temperature? Temperature, some books, they will tell you, oh, temperature is the degree of coldness or hotness of a body. That's correct. But the average kinetic energy of the particle in a body is temperature. So the two definition or these two description or explanation of given to temperature, they are all correct. It's the degree of hotness or coldness of a body or the average kinetic energy of a body. Both of them are correct. And is measured. The unit of temperature is measured in degrees Celsius or in Kelvin, represented with a K. Then we also look at internal energy. What is internal energy? Internal energy of a system or of a body. A body, an object. But when we talk about system, we're talking about an object or a group of objects that interacts. So now, you look at all of these. Internal energy talks about the total energy contained in a system. What is a system? A system is an object or a group of objects that interacts. So now, all of these, the heat is denoted with letter Q. The temperature is denoted with letter T. The internal energy is denoted with letter U, which is the total energy contained in a body. So now, let's look at the next thing we look at quickly is the amount of energy required. What's the amount of energy required to raise the temperature of an object? Now, when we are specific about the object, we're referring to a specific object. Then, what comes to mind is what is referred to as the specific heat capacity. Now, the specific heat capacity of a body is defined as the temperature required, the amount of heat required to raise the temperature of that body, that is 1 kg of that body, by 1 degree Celsius. That we are now specific. We'll talk about the specificity of the mass to be raised, 1 kg, by what? Specific temperature, 1 degree Celsius. So the quantity of heat required to raise 1 kg of an object by 1 degree Celsius is what is known as specific heat capacity. All these are terms that we need in thermodynamics. All these are terms that we need in thermodynamics. So now, because we're going to calculate the specific capacity of some objects today, or in our problem solving section, now we have a formula we use in calculating the specific heat capacity. Now, Q is what? It connects the heat energy required. You know, I told you it's denoted with letter Q, which is giving us M. M represents the mass of the object. The small letter C stands for the specific heat capacity. Then delta T stands for the change in temperature. This is the formula. Here is for heat. Here is for mass of the object. Here is the specific heat capacity. Here is the temperature change. Here is temperature change. This is a formula. And so we're going to use it. When we start to apply it, you understand what we are talking about. So all of these, they have their units. For quantity, the heat energy transfer, we use joules. For the mass of the object, we use a kg. For the C, which is the specific heat capacity, we use joule per kg degrees Celsius. Then for change in temperature, we use degrees Celsius. So now we quickly go again into explaining the first law of thermodynamics. What's the first law? What does it state? So when we talk about this first law of thermodynamics, the first law states that the total energy in a system remain constant. What it means is that in a closed system, there is no interaction, there is no energy change with the environment. And so the total energy in a closed system remain constant, no energy gain and no energy lost. And that can be represented with a formula. The formula to represent the first law of thermodynamics is giving us the change in the total energy, is giving us the heat energy in that system, and you remove the work done by the system. So now you remove the work done by the system. W represents the work done. Q represents the heat energy. And the change in the total energy is the heat energy minus the work done by the system. And so I also said we are going to just look at briefly the heat transfer method. How is heat transfer? As we have defined that heat, move from a place of higher level, a place of a hot object to a cooler object. How is heat transfer? There are different methods in which heat is transferred. It can be through conduction, it can be through convection, it can be through radiation. We have treated this before now. It's just a recap. All of these are under thermodynamics. Now, because today we are going to concentrate more on calculating the specific heat capacity of an object. So we are going to look at, let me bring back this formula. This formula, we'll bring it back again, calculating the specific heat capacity, which is Q equals the M the C, and the temperature change. Now, I've told you that these represent the heat, quantity of heat, mass, specific heat capacity, and the change in temperature. Now, I have, having summarized or recapped this, we have this now, which is the first problem we're going to solve, because if you look at the topic, we'll talk about calculations. So now, the first problem is on specific heat capacity calculation. The first question is how much energy? In this context, we're talking about how much heat energy is required to heat 2 kg of water from 20 degrees Celsius to 80 degrees Celsius, given that the specific heat capacity of water, which is small letter c, is equal to 4,200 joules per kg degree Celsius. Now, what's the solution? If you can remember this formula, then the solution is not far-fetched. So we go to application of this particular formula. Already we know that we're looking for Q. Q is unknown. So we put question mark there. Then M is a mass. The mass is giving us 2 kg. Then the specific heat capacity of water is given at 4,200 joules per kg degrees Celsius. Then the change in temperature. We said the change in temperature is from 80 degrees to 20, from 20 degrees to 80 degrees. What's the change? 60 degrees Celsius. So here we have all our values. So what we just need to do is to slot in the values. Slot in the values to the equation, the formula. So it will be equal to mass is 2 kg multiplied by 4,200 multiplied by 60. If you solve this, if you multiply it, you are going to get a very simple figure, which is we're going to get 504,000 joules. So 504,000 joules. Now, which is the same thing as 504 kilojoules. Is the answer in kilojoules and in joule. So this is the specific heat capacity required to heat 2 kg of water. 2 kg of water. This is the specific heat capacity required to do that. So now, is there any question before we move on? Okay, if there is no question then. Now, we are going to stop here for today. I have sent your assignments on the portal, so you can check it out and get it done. I've given you this because when we meet again, we're going to advance from here. So see you in the next class. Thank you.